Hey everybody, today we're going to be talking about partitions, and this is the kind of thing that when you really understand how to use partitions, it will really add a lot to your ability to solve probability problems. What are we talking about? All right. The first thing we learned yesterday was that when the intersection of two event sets is non-empty, we have inclusion, exclusion issues, and those issues escalate the more sets that are involved. And we had a formula, but it's certainly less complicated if we can have disjoint event sets. We don't always have those, but when we can, they're extremely helpful. So, what are we talking about? Well, and before we go too deeply into the definition, the deck of cards is a good uh, sandbox here, right? Because we have the partition of the suits, right? There's four subsets: the hearts, the spades, the clubs, the diamonds. And each of these subsets has these properties. First of all, they're non-empty, right? There's 13 cards per suit. They're pairwise disjoint. In other words, if it's in a heart suit, it can't also be in the spade suit, right? That it can only be in one of the subsets at a time. Okay. And the third thing is that the union is the whole space, right? The whole sample space. And of course, the suits, the four suits, do comprise the entire deck. So that's what we're talking about in terms of a partition. They're um, often implicitly built into a problem solving problem, into a probability problem. But the idea is that we can use these partitions and we're going to break down more complicated events into more easily digestible pieces. Okay, for example, if we have five seniors being added to the homecoming committee and the choice is going to be from three football players. Oh, wait. Um, we're adding seven. Wait, how many are we adding? I am going to have to sort this out. Five seniors are being added to the homecoming committee, three football players and four cheerleaders. That sounds like seven. If nine football players and three cheerleaders are eligible, how many different groups of football players and cheerleaders may be added? Okay, well, our subset is clearly the football players and the cheerleaders. We have nine of the football players, which we'll call set F, and we have seven cheerleaders. We'll call that set C. And on the right, you see a picture of these subsets, and do they form a partition? And in fact, they do. And so here we have an answer to our question finally. Why? Because 9 choose 3. What is this saying? This is saying we're going into the football part of the partition where there are 9 items and we're choosing 3 of them. Okay, so the number being chosen from is on top, the number chosen is on bottom. So 9 choose 3 is from the 9 football players, choose 3 of them. And then we're going into the cheerleaders subset and choosing 4. So we've chosen 3 football players and 4 cheerleaders. So this needs to be 7, not 5, right? We're adding 3 football players and 3 cheerleaders. And I apologize for the typo, but as you can see, we have this partition. It partitions the potential committee members into, well, there's 16 total, and 9 of them are in one subset, 7 of them are in another subset. And then we choose within one of the subsets, choose within the other subset, and multiply the results. So you'll see this theme reemerge quite often in probability problem solving. So let's check out some more ways this can happen. Okay, so one party in the Senate, they're attempting to set up a committee to meet with the president. They want 3 senators from east of the Mississippi and 2 senators from the west. If their party has 14 senators from the west and 17 from the east, how many different committees could be formed? Okay, this problem comes with a partition set up already, right? It's not just implicit; it's explicitly set up. The Mississippi divides the United States in half, roughly. Um, and we have 14 senators to the left side of the Mississippi and 17 from the right. We've got this obvious partition set up. Okay, so let's jump into our notebook. And again, it goes over this. Oh, we can evaluate this, right? So, um, hang on a second. What I don't have is the formulas for combinations and permutations. So I'm going to stop the video and be right back so we can add that in. I'll try to put that in on the data hub so that you guys will have it rather than having to type it in. Okay, so I'm back and I've added in the combinations and permutations so I can jump back into where we were talking about the football players and the cheerleaders. And all I'm doing is evaluating this expression so we know the answer. Okay, and let me get rid of that there. So, combin, and I'm going to do 9, comma 3 times combin and 7, comma 4. Okay, so there are 2,940 different ways to choose this subcommittee from these players and cheerleaders. Okay, so now to example 2 about the one party in the Senate is setting up a committee and how many different committees could be formed with these different senators. Okay, right, so remember, I'm going to use hashtag comments here. Um, um, in the West, right, we have 14 total. And sorry, I want to do from the East, they have 17 total, right? So what are we doing? Well, what we're doing is we're going inside the uh, Western states. And from those 14 senators, right, we're going to choose 2, right? It says 2 from the West. All right, and then we want 3 from the east, so I'm going to multiply that. I'm going to go into the east where there are 17 senators from the east. I'm going to choose 3 of those, right? They want 3 from east, 2 from west. All right. And so there are 61,880 different ways that that committee could be formed, right? We're just using the partition that's built into the problem. The problem kind of sets up the partitions for us as they describe the scenario. Okay. Here we have on a game show, a treasure is hidden inside a balloon. There are 80 red balloons, 55 blue, and 15 orange. Contestants have 30 seconds in a windy room to grab 2 of each color. How many different collections? Oh, that's kind of funny. There's, I believe, an extra F in different. There we go. How many different collections of 6 balloons are possible? Okay, well, we clearly have 3 subsets, right? We have 80 red, 55 blue, 15 orange, right? So what are we doing? We're taking 2 of each. So from the 80 red balloons, we're choosing 2, right? And from the 55 blue balloons, we're choosing 2. And from the 15 orange balloons, we're choosing 2. Okay, so again, 3 straightforward subsets of 80. The numbers inside, the cardinalities of those subsets are 80, 55, and 15. We choose 2 from each, and that means that we have a lot. This looks like what, 40? No, 492,723,000. Again, that's assuming we can tell the difference between all of the 80 red balloons, but or all the 55 blue balloons. But again, if they have these different treasures inside them or different things inside them that the contestants are trying to win, then yes, that's the total number. R is just lost a little bit on rounding error. Okay, that's an integer, not a real number. Not a decimal approximation. So Jody wants a puppy. At the pet store when she arrives, there are 11 Labradors, 3 Beagles, 5 German Shepherds. Jody's favorite puppy is a Beagle. If her mom, who's in a terrible hurry, buys 2 puppies that are different breeds at random, what is the probability that Jody gets a Beagle? Okay, so this is a somewhat ridiculous scenario that the mom's in a hurry. She's just going to buy 2 of different breeds and hope for the best. And again, there isn't an explanation in the question as to why Jody just doesn't tell her mother, which, she would prefer. Um, but okay, so what do we have to do in this probability question? First of all, we need to count the total possibilities, right? That's going to be the denominator of our probability. And then what's the next thing we're going to have to do? We're going to have to count the total number of outcomes that include a beagle, which is the dog that Jody would prefer. Okay. So to count the total, possibilities for the moment, what is that? Well, we have these 3 subsets with 11, 3, and 5 things in them, right? 11 Labradors, 3 Beagles, 5 German Shepherds. So combine 11, choose 1, right? We're choosing 1 from each. Her mom is only going to choose 1 of each. So we have 11, choose 1. And then we have 3, choose 1. And then we have 5, choose 1, right? So that's the total number of possibilities, which just to evaluate that, there are 165 different possibilities. And you'll notice, by the way, that that this combination, 5 choose 1, there's 5 of them, and 3 of these, and 11 of these. So if you multiply 5 times 3 and get 15, then 15 times 11 is 165. All right, so this is kind of odd. The mom has chosen a way that's going to provide 165 different possible outcomes, the number of outcomes that include a beagle. Well, how would that work? Well, remember, she's buying 2 dogs, so you could have the one where she gets a Labrador and a Beagle, just 3 choose 1. But the only other way to do this that contains a Beagle is to do a German Shepherd and a Beagle. Okay. And why am I evaluating this? Well, it would be nice if the number that just appeared on the screen was smaller than 165. Why? Well, because I'm creating a fraction and probabilities have to be between 0 and 1, so I'm hoping that I don't get a bigger number. And sorry, this isn't quite right because I needed to pick the Beagles. Combine 3 choose 1, right? So using the partitions to do German Shepherds and Beagles and adding that to using the partitions to do a Labrador and a Beagle. Okay, and still 48 is less than 165. We're looking at roughly a 25% chance, but now we have everything that we need. So let's do it this way. The probability that we're calculating is equal to, right, all of this divided by this, but we need to put parentheses around it in the denominator. Why? Well, do we need to not? Let's put parentheses in the numerator too. Why am I doing this? I'm not exactly certain how the order of operations is going to go, but I know that this will count them correctly. So why don't I just do it this way? And you'll notice that we don't have an answer. Why? Well, at calculated probability, what we do is we type, oh, and I want that to be lowercase p just so I can type it better. Probability, I put the name of the variable underneath the expression that assigns the variable, and that gives me the correct answer. And the correct answer is that there's a little more than a 29% chance of Jody getting a Beagle with this messed up method of selection. Okay, so one of the interesting things about partitions is they really help us with these probabilities of different poker hands. Why? Well, because four of a kind, for example, well, we're talking about kind, those are values, and there's a value subset, right, that is shown to you right here. Okay, sorry, I'll have to come back and look at it, right? This is uh, the figure shows these 13 value subsets. Each of those values has four cards, right? They're four suits, so there's four cards. There's four eights, there's four nines, there's four jacks, there's four kings. Okay, so what do? We choose at both the subset level, the partition level, and we choose at the card level. And I'll explain that in just a second. Let's jump back and look at the right. So these are not all of the um, poker hands. You'll notice that the straights and straight flushes haven't been counted. Well, we don't really use partitions to count them. Okay, we can calculate those. It's not that hard, but we don't tend to use partitions um, in the same way. So let's jump ahead. Okay, and we're doing this four of a kind calculation. So what are we doing? The first thing we're doing is a partition pick. We're going inside the partition. There are 13 subsets to choose from, one for each of the values, right? So 13 choose one goes in and picks like, oh, we're going to have the value of 5. We're going to have four of a kind. We're going to have four fives. Okay. So the 13 choose one picks in the subset, picks which subset in the partition we're using. Then 4 choose 4 inside that partition, right? Chosen the partition here. Inside the partition, we choose four cards. We need all four of those four cards. Okay, what's going on here? 12 choose 1. Well, there has to be another value in the hand. Okay, so let's just say that the other value we're going to have is an ace. So we're going to have four fives and an ace, right? But again, that comes from the 12 choose 1. There's 12 remaining values that weren't used. So I'm going to pick one of those, and then inside that subset of the partition, I'm going to pick one card. Okay, so let's jump over to our probability of drawing four of a kind, right? What do? 13 choose 1 to choose the value, subset. And then inside that subset, choose all four cards. And then I'm going to pick another value subset that's not the one that I picked for the four of a kind, right? And I only need one of those cards, so 4 choose 1. And you'll find that there are only 624 four of a kinds. Okay, so we can clean this up slightly. Let's do this. Okay, so let's call the subset 4. Okay, 4 equals this, right? And this is going to be the number of four of kind hands, right? We're calling it 4, and we're going to print out the subset, excuse me, the cardinality of that, right? But also we need the total number of poker hands. Okay, so let's just call that total. That should be fine, right? What do we have? Well, from the 52 card deck, we're choosing 5 cards, right? So the total, the denominator is always 52 choose 5, which is about 2.6 million. And there you see 2.6 million. Wait, sorry, what have I forgotten? Again, I need to tell it, hey, show me the total as well. And it prints out both of these numbers for us. Again, it's an integer, not a decimal number, but 2.59 million, 2,598,960. Okay, so we're a few we're a few hands shy of 2.6 million, but rounding there about 2.6 million hands. Okay, so then what's the probability? And I'll just say that P equals, right, this This is generally how we do it on a a test paper or quiz paper, and we're dividing by then 52, choose 5, and always forgetting to print out the variable after assigning it. And what's happened here, order of operations doesn't appear to be working, right? Because clearly there's not a 47% chance of a 4 of a kind. So let me make sure that we add this in. And I am not sure what I'm doing incorrectly here. With this evaluation and without time, what I can do is I can say, look, we know that up here we had 624. And yeah, this is weird. This is clearly doing something that I'm not expecting, but we can do the 2.598960. There. I'll take a look at that and see if I can figure out exactly why it wasn't working. Um, but when you do that probability, you find out that there is, what is that? Tenths, hundredths, thousandths, 2/10,000. So 2,400 thousandths is the chance of that happening. Okay. Now, probability of a flush is going to work the same way, right? What are we going to do? Okay, so we're going to pick from the partition, from the suit partition, right? We need one suit. Because that's what a flush is. A flush is a hand that has all hearts or all spades or all diamonds. It has no other suit. It just has the one. So when we're picking from the suit partition, let's just say flush equals, and what are we doing? We're doing 4 choose 1. Okay. And by the way, that is just 4, right? What are we doing? Well, we've got 4 things to pick from, and we're picking one of them. There's 4 ways to do that, right? But once we're inside, once we've chosen whether it's going to be hearts or diamonds or clubs or spades, now we have to pick the cards, which is what? It's 13 choose 4. From the 13 cards in whichever of the suit I've picked, I do have to pick, 5 cards, right, to complete the hand. So how many flushes are there? There's 5,148 flushes. Okay. And again, we're dividing by the same thing. So I'm just copy pasting from up here. Why? Because this, let's call it prob, equals, and then 5148 divided by the total number of poker hands. And so we find out that there is about a 0.2% chance of drawing a flush. Okay, it's more likely than drawing 4 of a kind, but still pretty rare. That's why flushes are extremely powerful hands. Now, the probability of drawing a full house, and I want to look back for a minute at this subset. Why? Here's the problem, right? What is a full house? A full house in, let's just say we have aces and eights. And you can look this up. I believe it's colloquially known as the dead man's hand, and you can check out if that's right. Okay, so a full house is something like ace, 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 8, 8, where I have a 3 of a kind and a pair. Okay, but then check this out. What about this? I could have eights full of aces where I have 3 eights and 2 aces. And these are very different hands. The one I wrote on top is actually would beat the one on bottom, right? Aces full of eights beats eights full of aces. The 3 of a kind value is the first thing that gets compared. And then the 2 of a kind, or the pair, is the next thing. Okay, and why do I tell you this? Because That's going to make it hard. We are not going to do 13 choose 2, or if we do choose 13 choose 2, we're going to create ourselves a problem with this. Why? Because 13 choose 2 picks the aces and the eights, right? But it doesn't differentiate as to whether I'm doing 3 aces or 3 eights. Okay, so if I do 13 choose 2, I'm gonna only count half of the full houses, okay? And I'd like to count them all. So let's jump over into our notebook in the data hub, right? The probability of drawing a full house. Okay. So what are we gonna do? All right. Um, Actually, this is fairly straightforward. The probability is equal to what? So combine. Let's just do 13 choose 1. What are we picking? We're picking the 3 of a kind. So 4 choose 3 is the number of ways. Once I've picked the value for the 3 of a kind, then I choose the 3 cards. Then I can do 12 choose 1, right? Why? Well, because there are 12 values that weren't used for the 3 of a kind that could be used for the 2 of a kind. And that's 4 choose 2. Okay, and that's not a probability yet, but you can see, right, that this is slightly less likely than the probability of drawing a flush. That's why a full house beats a flush. Why? It's more rare. Okay, and then I'm dividing by the total number of poker hands, right? And so that probability is 0.144% chance of happening. Again, not real likely, but you can see why it's a valuable hand. But I want to be careful. Why? Because if I did this in a slightly different way here, let me get rid of here. I'm going to hashtag out the denominator. Why? I want to compare that number to the number where I do it wrong. Okay, I said we don't want to do 13 choose 2, right? If I try to do all the partitions at once, let me call it prob 2 here for just a second. Okay, and then let me just show you that if I do prob 2 times 2, cha-ching, I get the right thing. Okay, what's going on here? Well, if I pick the partitions this way, I've picked 2, and one could be the higher value, I mean the 3 of a kind value, and one could be the pair value, but I haven't picked which is which. So there's actually a second thing going on here. If I do it this way, I have to do 2 choose 1, because from the 2 things that I've just picked, right, from the 2 subsets of the partition that I've just picked, I have to pick one to be the 3 of a kind, and then the other will be the pair. All right, that's why we've undercounted, right? We've counted exactly half of what we needed to count. All right. So this one is incorrect, unless, well, this is correct now that you know what you're doing. But the approach can get you in trouble. So I was suggesting this way, where I choose 13 choose 1. I choose the 3 of a kind first, pick those cards, choose the value for the pair next, choose those cards, and I get the right answer. Okay, this is actually correct now that I've put in the additional 2 choose 1 after the 13 choose 2. And I do get the exact same thing. And then taking this out, taking the comment out, I get back to the probability. Same thing, this will be a probability. So there's 2 correct ways to do this, but you have to understand, and let me just jump back. Well, let me just say this. There are times when we can do 13 choose 2 to get the 2 different values. Okay. But there are times that we can't. And when can we? Well, the times we can are when we're drawing 2 pair. Why? Because ace 8, 8, 8 is the same as 8, 8, ace 8, ace, right? It doesn't matter whether I have, whether I draw the aces first or the aces second. The hand is still the same. Okay. So to just quickly do that one, right, we'll do a Let's call it TP for two pair. Right? So we can do combine 13, choose two, right? So we have two pairs and they're the same thing that we're drawing, both choices. We're going to choose the same number of cards, right? So 13, choose two gives me the two values for my two pair. Okay, and then inside the first one, I am going to do 4, choose 2. Now, you can do a squared here. I'm just showing this. It kind of makes sense to me. I'm picking the two values inside the first value. I'm picking two cards inside the second value. I'm picking two cards, right? And then what? Oh, well, then there's this 11, choose 1. Why? Because there has to be another value in the two pair. What I can't do is I can't go, oh, I've picked two cards, so 50, choose 1. No, because then I could get a full house. One of these values could get repicked, right? So I do 11, choose 1 times 4, choose 1. And the 11, choose 1 forces me to be picking from a different value than the two pair came from. So this is going to be the probability of drawing exactly two pair. Okay, and then, sorry, this is the number of ways it can happen. All right, and what are we doing? Same as before, we're just copy pasting that denominator. Actually, let's see if this is working now, because I'm kind of baffled by this, the way that's not working correctly, right? So I'm going to go with the value. And I guess with these combinations, the order of operations doesn't work quite like I think it should. And we have just slightly less than a 5% chance of two pairs. So that's kind of cool. All right, and what are we doing here for three of a kind? Let's call that TK for three of a kind. What are we doing? Well, we're going to do 13, choose 1, as you're getting used to. That's going to pick the value for our three of a kind. And then inside that subset of the partition, there are 4 cards. I'm going to pick 3 of them. Okay, and then I'm going to do 12, choose 1, Y. Excuse me, 12, choose 2, Y. Well, I need 2 other cards, and they can't match each other, or I have a full house. And they can't match the 3 of a kind, or I'd have 4 of a kind, right? So the 12, choose 2 is picking 2 different values to make sure that I have exactly 3 of a kind and not a better hand. Okay, so 12, choose 2 times. Okay, inside the first value that I've picked, I pick a card, and then inside the second value that I picked a card. And again, I'll show you down here what I didn't show you up above. I can just do squared, right? It does make sense that way. And then the 3 of a kind is, there's almost 55,000 of them, right? And then I can divide those by the total number of poker hands. And you can see that I have about a 2.1% chance of drawing 3 of a kind. And finally, drawing a pair. Well, I need to pick a value for the pair, so that's 13, choose 1. Sorry, not 13, choose 10, 13, choose 1. And inside that, I'm picking 2 cards. Inside that subset of the partition, I'm picking 2 cards. But now what am I doing? I'm doing 12, choose 3. Why? Well, from the other 12 values that didn't get used for the pair, I've got to pick 3 unique cards. Why? Because if they match each other, I have either 2 pair or a full house. Or if they match the one that I've chosen for my pair, I've got either 3 of a kind or 4 of a kind, right? So I need to pick from the values that weren't used for the pair, and I need 3 unique values from those remaining 12 so that I don't end up with a better hand. So the probability of drawing exactly a pair then is going to be combine 4, choose 1, but I do that 3 times. Right. And so that means that there are almost a million one pair, or over a million one pair hands. Okay. And then dividing by the total number of poker hands, we realize that there's about a 42% chance, a little more than a 42% chance of drawing 2 pair. Okay. So just to remind you, right? This is a partition level pick, the 13 choose 2. This is actually selecting 2 cards from the first value and then 2 cards from the second. Again, I go back to the partition level to get a different value than I used for these card picks so that my last card pick is from a different value and I get exactly 2 pair. Just to run through that again on a different one, full house, right? 13 choose 1, that's a partition level pick. It picks a subset, a value subset, and inside that value subset, I choose 3 cards. Then I pick a different value subset, and inside that subset, I pick 2 cards. Okay, so what I'm emphasizing here is as you're using the partitions, you've got to remember that if you're picking a partition, you haven't picked any cards yet. Once you pick the subset out of the partition, then you go inside the subset with a second choose notation, a second combination to count the number of things that can be chosen. All right, so partition, then pick the cards, and then a partition pick, and then pick the cards. That's how we're proceeding, and it helps to keep that in mind as you're working through this.